as I mentioned before, it bothers me when I have to grab a calculator for something, because usually I go way too fast. I hit a button I'm not supposed to hit, all of that kind of stuff. So operator error is going to happen. It just will. So if we can, we want to evaluate things by hand, that it's possible to evaluate by hand. But when we do need to use the calculator, we have to know how the calculator works so that we're getting what we want to get. So, should anybody need to borrow a calculator today? One of the most commonly goofed up things when you're using the calculator is you have it in radians mode and you're talking about degrees, or you have it in degrees and it's supposed to be in radians. So that's one of the things you want to consciously think about before you grab the calculator. Okay, did the information about this angle come in radians or did it come in degrees? And then, how do we know stuff is wrong? Well, if we put sine or cosine into the calculator, we're supposed to get a number between 0 and 1. And we talked about that yesterday, about how you're always taking something that's shorter and dividing it by something that's longer because the hypotenuse is the longest side. So it should always be between 0 and 1. So if we see a negative, we know we're wrong. If we see 2.75, we should know we're wrong. That way we'll catch ourselves with that. And then we have to know the difference between using the inverse key versus using the reciprocal. Because when you look at your calculator, you're not going to see buttons for cosecant, secant, and cotangent. They are not there. What we have to do is get the sine of the angle and then flip it. Take it to the -1 power. And that would give us cosecant. So when you punch something in and you want the cosecant of that angle, I'll just make one up here. We'll do 36 degrees, something that's not real interesting. So if we take the sine of 36 degrees, we want the reciprocal of that, cosecant. So we hit the button that says, it's just to the left of the sine button, x to the -1. And that's going to flip that answer over for us. And if we need secant, we're going to use the calculator to do cosine and then flip it. And if we need cotangent, we'll use the calculator for tangent, and then we'll flip it with that x to the -1 button. So whenever we need those secondary trait functions, that's a button that we're going to count on for that. So I'm looking at this and it says evaluate that cotangent of 30 degrees. And I realized, well, I'd have to find the tangent of 30 degrees first, and then I'd have to flip it. Tangent of 30 degrees first, and then flip it. So this is the right one. Now, it's been a long time since you had geometry, but this says inverse tangent. It doesn't say take the inverse of the value. And inverse tangent means I want to know what angle gave me this. Which angle had a tangent of 30? So what we're actually getting here is the angle that made that happen. And that's not what we want. We want the trig value. And the trig values are the ratios of two sides in a triangle. So this one is definitely a no-go, because we're not working backwards to figure out the angle. What we want to know is the cotangent of 30 degrees. So that's another error that happens quite a bit, putting that x to the -1 in the wrong spot. Or a lot of people will look at that and say, oh, wait a minute, that -1 piece, it's right above the sine key, the cosine key, and the tangent key. Those are for working backwards to find angles. It's a totally different concept. We will get to that eventually, just not in this early step. So the other things, using function shorthand that the calculator does not recognize. It's a calculator, it has its limits. So this error is less dangerous because it usually results in an error message. The calculator will yell at us, you can't do this. We will often abbreviate powers of trig functions, writing sine cubed of theta minus cosine cubed of theta instead of, and it's mostly because of the parentheses. It just becomes a big hassle to put all those parentheses on there. So we'll generally shorthand these pieces, but the calculator would not acknowledge that. It would not use those. So the calculator doesn't recognize the shorthand notation and yells at us for a syntax error when that happens. But we're not going to use the calculator a whole lot for those types of things anyway. So not closing the parentheses, that's another big no-no. Sine of 30 degrees, 1/2. We get it right here. Now with this one, the calculator is going to say you want the sine of something, and it gives you the parentheses so that you can tell it what you want and then put another set of parentheses on there. So the calculator at this point is going to tell you what the sine of 32 degrees is, because it doesn't know where you wanted it to end. It's going to go ahead and do that addition for you and say, hey, this is the sine of 32 degrees. Whereas if you finish off those parentheses, it's saying, here's the sine of 30, now I'm just going to add 2 to that and get the answer. So you have to tell it explicitly what you want it to do, and be careful to close off parentheses when you're touching these things in. So like it says, we've got a correct and incorrect way to find the sine of 30 degrees plus 2. This is not going to do it. Right there in the middle. So careful when we need to use the calculator. And like I mentioned, we're not going to use it a whole lot anyway, because what we'd like to do is have exact answers, and it's impossible to find exact values on a calculator when evaluating trigonometric functions. So let's say we're looking for the sine of 60 degrees. First of all, bells and whistles should be going off in our brain. I should never be using a calculator for the sine of 60 degrees. I can use my special triangle, I can get what I need, and get the square root of 3 over 2. But if you accidentally use your calculator, hopefully bells and whistles would go off, because if we use these numbers enough, we start to recognize, oh, wait a minute, 0.866, that's the square root of 3 over 2. I'm not supposed to use the calculator. Hopefully, we won't get to that point, because we'll be using the calculator so little that you wouldn't recognize it anyway. But, and of course, like college trig, that happens quite a bit. You know, you're working through a really long problem, and all of a sudden you get 0.866, and you go, oh, it's the square root of 3 over 2. Yeah, let me go back and look at this a little different way. You know, let me use my special 30, 60, 90 triangles to work on what I have here. So this says, show why the following trigonometric identities are true. And because we have had so few days when we're going to have work time and time when I can have you work with partners, because we have so much material to cover, I decided this would be a good one to do that with. I'm going to do the hardest one with you, and then send you with a partner to figure out the other two. And the hardest one we have is right down here, number 3. This is one of the most basic trig identities that we have. Sine squared theta plus cosine squared theta equals 1. But we can't just say, yes, this always works because the book told me so. We have to see it with the definitions. So with the definitions, I'd say to myself, sine, that's opposite over hypotenuse. So they're telling me if I square that and I add, let's see, cosine is adjacent over hypotenuse, adjacent squared over hypotenuse squared, that's supposed to work out to be 1. Huh. All right. Well, it's fractions. With fractions, if you have a common denominator, you're supposed to be able to put them together. So let me write it and see what happens. Maybe I'll come up with something. Opposite squared plus adjacent squared over hypotenuse squared equals 1. Okay. I'm still not seeing it. Maybe it's because I'm not seeing it. Opposite squared plus adjacent squared. This squared plus this squared equals what? This squared by the Pythagorean theorem. So these two sides, when you square them and you find their sum, they actually give you that. Well, hey, I can replace my numerator. Hypotenuse squared over hypotenuse squared equals 1. Well, of course it does. Is 1. Now this was the toughest one because it generally takes the picture for people to be able to say, okay, now I get it. Opposite squared, it's just the two sides. That's all it is, the two legs of the triangle. The others are fairly basic to do just with your definitions. So just your SOHCAHTOA, opposite, adjacent, and hypotenuse. So go ahead and get working on 1 and 2. And this is the first time for candy partners in here. What's going to happen is everybody's going to get a piece of candy. You're not allowed to trade the candy because that candy knows who your partner is supposed to be for the day. It's magical. It knows that. And when everybody gets their candy, I'll ask you to raise your candy up in the air. You'll make eye contact with the person that has exactly the same candy as you do. You'll get up, you'll find a spot you can sit next to each other, and you'll talk through these problems together. But in the meantime, go ahead and work through 1 and 2. I did not get anything from the nurse telling me that anybody in here was allergic to nuts. But since that's such a big deal, is there anybody in here that I should know about and be careful with? All right. Flying at me here. And I realize some of you aren't done. That's okay. You're going to have a partner so you can communicate. We remember 90% of what we teach to somebody else. So communicating is really effective in remembering your learning. Candy up in the air, please. Make eye contact with whoever it is that has the exact same candy as you. And then get up because somebody wants your seat and go join them and talk about what you're doing and what they're doing. If you can't find your partner, come to the front of the room. You'll probably meet each other here, because that's usually what happens. Oh, after you have your partner, you can eat your candy. If it's something you absolutely can't stand, there's always a bucket up here to trade 1 for 1. If it's something you just can't do. Anybody need more time? All right, I'm going to use a little bribery here. I've got another piece of candy for somebody who's willing to talk us through what they did on number 1. Art, what'd you do?
Well, I wrote it out as hypotenuse over opposite first.
Oh, you started over here.
Cosecant equal. opposite over hypotenuse over opposite equals 1 divided by opposite over hypotenuse. Then to figure out what 1 divided by sine was, I took 1 times the reciprocal of sine, which is cosecant.
Like so?
Yeah.
Okay. And Art actually did a little bit more than he needed to right here, because you could just leave this cosecant theta, and then once you get to this point, realize, oh, that is cosecant theta, hypotenuse over opposite. All right. How about number 2? Again, piece of candy.
So I did opposite over adjacent. And then I did opposite over hypotenuse multiplied by hypotenuse over adjacent.
Okay, so you just went immediately to multiplying by the reciprocal. Warning though, on the test, don't skip steps. If you do that, we're gonna have to take something off. All right, so intermediate step there, we've got opposite over adjacent equals opposite over hypotenuse times hypotenuse over adjacent. Okay, got that far?
And then I just multiplied
Basically canceled out your hypotenuse, right? And again, you would not necessarily have to do this step right here. You could just work with one side of this and make it equal tangent. And later on, when we work more with the trig identities, we'll always do that, where we say, okay, I'm going to leave this one as it is, and I'm going to show that this one will come out to be what that is. But this is definitely a helpful step right now, especially as we're just starting out to realize, hey, this is what I want to see on the other side. This is how I'm going to know that I have tangent. So we're using definitions to figure this out. And do you see why I wanted to do number 3 together with you? About how different that is. I mean, it's that visual, that little extra piece that gets you through that third one that you don't necessarily need with 1 and 2. 1 and 2, it's just the definitions. So a triangle has 6 parts. We've got 3 angles and 3 sides. When we find all of those, that's called solving. And that's something you did back in geometry as well. It's just been a long time since you've done it. So when you solve a right triangle, you're finding everything you possibly can. So with this one, we've got a right triangle with a hypotenuse of 8. Includes a 37-degree acute angle down here. Find the measures of the other 2 angles and the lengths of the 2 sides, which they could simply have just said, solve the triangle. They didn't have to be so specific. So the first thing I do is go after the easiest thing. I mean, we know this is 90 and this is 37. How hard can it be to get the other angle, right? Because triangles have how many degrees? Tell your partner how many degrees are in every triangle. Thank you, 180 degrees. So 90 is gone for this angle. We just really need 90 minus 37. 53 degrees, but we need to label. We need to say, hey, that's the measure of angle. And now here's where we go back to a little geometry as well. Lowercase letters are always opposite the vertex that has the uppercase letter. So if this is little a, right across from it there has to be big A. And if this is little b, that has to be big B up there. So we now know the measure of angle B is 53 degrees. But we don't want to use that when we do our math. Here's why. We might have goofed up. And if you goof that up and you use that information for the next 2 steps, now you have all 3 parts of this problem wrong. Because we have our angle, that was the only other thing we needed to find, but we still have 2 sides we're supposed to find. So what we want to do is go back to what they gave us, the original information, and use that to find what we're missing. And that means That's the angle I'm gonna focus on. And I can't do A and B at once. So what I'm gonna do is find them one at a time, and I'll just go alphabetically. This would be opposite. And the other information they gave me was the hypotenuse. So I think its trig function uses strictly opposite and hypotenuse. Tell your partner which trig function, opposite and hypotenuse. So the sine of 37 degrees is going to equal A over 8. Remember, the sine of 37 degrees is stuck in our calculator. It's just a number. So to solve for A, all we're going to have to do is multiply both sides by 8. So 8 times the sine of 37 degrees equals A. Now, there are many ways for me to goof this up punching it in. I want you to tell your partner what's the first thing we should check before we begin punching this in. If you don't have a calculator, you can just follow along up here. So mode, usually set in radians. I got lucky. Mine's in degrees right now. But they usually go back to factory setting is radians. So I'm going to want 8 times the sine of 37 degrees. 4.815. And that reminds me, on the homework, I should always see you rounding to 3 decimal places, okay? The book doesn't do it, but we know we're supposed to because the AP exam requires that 3 decimal places. So I'll have everybody round to 3 decimal places just so that we're always all doing the same thing. All right, we have A. I know what this is now. It's 4.815. I might have messed up on that too. So I'm not going to use the Pythagorean theorem because if I mess that up, then I'm going to mess up B. I'm going to go right back to my 37-degree angle, which was given to me. And this time I'm going to focus on B, which is adjacent, and the hypotenuse, because those were pieces that were given to me. So we're going to need a trig function that just uses adjacent and hypotenuse. Tell your partner what that is. So the cosine of 37 degrees equals B over 8. Multiply both sides by 8. And plug her in. .389. And if we had labels, we'd go back and make sure we have the labels. Now, there is and there isn't a way to check our answers. I want you to communicate with your partner, see if you can come up with a way to check our answers here. So eavesdropping, I'm hearing the Pythagorean theorem, but tell your partner what the problem with that might be when we punch it in. Does everybody expect that if we punch in 4.815 squared plus 6.389 squared and take the square root that we will get 8? What's probably going to happen? Probably going to be a little rounding error. And that's because we rounded these 2 pieces of information to get that. But the math is sound, you know, and like I said, we've got time. I'll go ahead and do that. 4.815 squared plus 6.389 squared and the square root of that answer. And we can already see it's going to be off a little. But it's 3 decimal places because our rounding was 3 decimal places. So we can kind of check our answer and make sure it's going to work. Now, if at any point I had said, I'm not going to go back to the original information, I'm always risking that if I made a mistake, that mistake is now traveling with me all the way through the problem. So it's always a good idea to go back to the beginning and use the initial information. Which brings us to the highlight of our day, a word problem. It's not really a word problem because there's a picture. So, like it says, real-world applications involve indirect measurement. Those are frequent. Anytime you don't want to measure something because it's too high, it's too long, you're not going to give somebody a measuring tape and say, here, climb the water tower, I want to know how high it is. You're not going to do that. It's dangerous, it's not gonna happen. How wide is the Mississippi at this point? You know, here, I'm gonna hold the measuring tape, you row to the other side. No, we don't do that. So what we do is indirect measurement. And even though it's a word problem, I know you can do this one. So you and your partner work together and figure out the answer to example 6. If you need to go back and grab your calculator from your desk, feel free. Then you'll put it together.
These word problems are so hard. I wish we had an entire assignment on it so I could get better.
Oh, you did a couple of them. You did a couple of them. Yeah. Just to make it a little more tricky, please convert your decimal into inches. So give me blah, blah, blah feet and this many inches. We'll just go to the nearest inch.
1.5.
Don't leave your partner in the dust. I do see a couple of people that use different trig functions than I would have picked, so doesn't mean they're wrong.
What did you get? I got 729. I took tan 65, then times it by 3 since tan angle equals opposite over adjacent. Yeah, those, they use H for some weird reason.
$729.132. So 729, we'll put approximately 729 feet. How many inches if we round to the nearest inch?
1,750.
2 inches. The 0.132 times 12, because there are 12 inches in a foot. Well, I could make up another example if you would like one. Well,
Not just one, we need
43210
at least two.
How you feeling? Our objectives of using this in real life was this last objective.
I think we need a few more things.
Tell your partner thank you for their wonderful help.
See your own.